Hello, my name is Dr. Cristina Hickman, and I wanted to thank the Sociedad Peruana de Obstetricia y Ginecologia for the invitation to join your annual meeting. So today I'm going to be talking about artificial intelligence for embryo selection. So these are my disclosures. I am currently the Vice President of Clinical Affairs for Fertility. I'm also a consultant for IVF professionals. I'm the Chief Scientific Officer at City, a lecturer at Imperial College London. I am a co-founder of a new clinic in London called Area Fertility, and I'm also a shareholder at Tomorrow. I'm also one of the organizers of the conference that's going to be held in Croatia. This is going to be held in Dubrovnik from the 15th to the 18th of September. And if you're interested in artificial intelligence and fertility, I invite you to come and join us in Dubrovnik. And the website for registration is aifertility.org. So artificial intelligence comes from the marriage between computer science and mathematics and statistics. So when you bring these two together, it kind of opens up a whole array of tools that are now at our disposal, which will assist us with symbolic learning, deep learning, data mining, decision trees, all the way to neural networks and computer vision. They have different levels of complexity between these different tools, and some of them are built in such a way that we don't quite understand how they work or how they make the suggestions that they make. How is a decision achieved? And this is the black box of artificial intelligence. We can assess the efficacy of prediction, but we are not entirely sure how it reached that prediction. No, it's not just prediction that AI can help us with. It can also help us with classification as well as improvement in efficiencies. When you bring these benefits together, it brings an opportunity for us to automate certain aspects of our job, which are not the ones which we enjoy the most. Things like the administrative aspects of our job. And when we automate these steps, we now bring a reduction in risk and error. We can bring increase in consistency, and that increase in consistency and reduction in risk can ultimately lead to an increase in efficacy. So there's a potential that AI can help us maximize the chance of pregnancy for each individual patient at a global level. So I'm going to give a few examples of how artificial intelligence is used in fertility. In particular, I'm going to be focusing on embryo selection. So I've done a lot of work both with City and with fertility around artificial intelligence. I wanted to show you some of the work that we're doing. So one of the things that we want to use AI for is to identify new biomarkers within the embryo that we can't see today with our eyes. So here's an example of how we look at a time-lapse time point of a particular embryo. The image is taken at different focal planes, and we can move up and down the focal planes to try and recapture in our minds what is this embryo meant to look like three-dimensionally. Now, we only get a few focal planes to work with, and what's in between, we kind of try to fill in the gaps with our brain, but we try to replicate this using artificial intelligence. And in doing that, what we did is we asked it, look, here's the top plane and here's the bottom plane. Tell me what the middle plane would look like. So the AI suggests is the one in the bottom left is what it suggests the in-between of the top two slides should look like. The actual in-between slide is on the right, and you can see that they're very similar. Now, if you keep asking that question again and again and again, we can recreate an infinite number of images, all stacked rather than just the 7 that our time-lapse incubator provides. So we can regenerate artificially all of the images and put them together to recreate the embryo using virtual reality now. What does it look like? We can now turn the embryo virtually to see what does it look like on different aspects, and it can give us a different perspective of what this embryo is. It will help us define, is it a cell or is it a fragment? Particularly with these large fragments that kind of resemble cells. And we can use this technology to track, not just visualize at different perspectives, but track the individual cells as we go through development and better understand the contact points between these cells. So we've been focusing our work at the 4-cell stage, and we have identified a number of different cell configurations that the cells have relative to each other. So we knew the tetrahedra, we knew the planar, but we have identified a number of other cell configurations which have a direct impact on the amount of contacts the cells have with each other. Our intention is to then use AI to quantify for each individual cell what is the level of cell junction, the degree of a cell adhesion between these cells, and where there is a separation, what is the intercellular distance. Now, this is something we would never be able to do with the time that we have in the lab, but a computer could do this automatically for us. So what do we have today? So the work I've shown you just now is something for the future, but what do we have today that is in existence that we can already be using clinically? Well, there's a few AI tools available in the market, and I've had experience with quite a few of them. I'm going to highlight a couple here of what they look like in my data set. So this is from the work that I conducted at ARIA. And what we did was, for the first few embryos that were biopsied, we sent them to Erica without telling them which one is aneuploid or which one is euploid. And we asked them to predict to us and tell us which one they thought was aneuploid and euploid. And they gave us the grade, which is optimal, good, fair, and poor, based on the Erica labeling. And we can clearly see here that the AI was able to segregate, not with 100% accuracy, but fairly good accuracy levels, which embryos were aneuploid and which ones were euploid. We did a comparison based on these embryos with all the different methods of embryo selection. So we have the established ones here, the morphology and the time lapse. We have here the time-lapse assessment using Cruz and Basile, which are algorithms that we now know are not generalized between clinics, and clearly demonstrated here in our data set. These algorithms don't work in our data set. But we also looked at non-invasive PGTA using Embrace. And it was very clear for us that Embrace was the one that most closely resembled the results from the PGTA invasive biopsy. Erica got second place, followed closely by the time-lapse assessment, and then morphology, and lastly by time-lapse, the algorithms that we have just discussed. So effectively, AI here has shown tremendous promise because it brings several benefits that some of these other methods of embryo selection don't provide. So for instance, PGTA and non-invasive PGTA require that we send the samples for analysis, and we don't get an immediate response. So we have to wait for response to come back for a few days, which means that a fresh transfer is no longer an option. Converting the patient to a frozen transfer brings extra cost, brings extra work, which are the type of things that we're trying to avoid when we're trying to improve access to treatment. So in addition, biopsying the embryo is invasive. And although can be done safely, we have numerous publications now that demonstrate that it is a risk when we expose an embryo to biopsy, and we are reliant on the embryologist's individual skill down to each individual procedure to ensure that the embryo viability is not compromised by the procedure itself. We also have the challenge of price. And PGTA and non-invasive PGTA are the most expensive ones per cycle. Time-lapse is expensive for you to introduce the technology, but once the technology is introduced, the price per cycle over time is actually very moderate. And morphology, obviously being the cheapest, however, brings the highest level of inconsistency between practitioners when comparing with the other methods of embryo selection. AI brings the best of all worlds. It's non-invasive, it's consistent, it's cheap, you get an instant result. And ultimately, the bit that we need to prove is, does it actually predict outcome? Now, there are a number of publications out there already that have demonstrated the benefits of AI. We don't have consistency between them in terms of the methodology. Some of them use time-lapse, some of them use static imagery, the type of data input, whether it was images alone or whether they have included demographic information about the patient or any lab settings or any additional annotations coming from the embryos. The outputs that they looked at, whether it was ploidy, fetal heart, live birth, or just a beta HCG, also varied. and the type of embryo population, whether it was blastocyst transfers or whether it was day 3 transfers, and ultimately the type of performance metrics to demonstrate that the AI is effective also is inconsistent. We have very different metrics being used in different publications. So what we need to do is try and bring in some consistency in how we're making these assessments and how we're communicating these assessments. But one thing all of these papers have in common is that all of them demonstrated that AI is effective, if not equal to an improvement over the current human assessment, the current methodologies that we're using at the moment. So one of the papers that I wanted to bring to your attention was looking at the level of seniority of the embryologist, and then by how much did AI improve the prediction compared to the human. And what was clear is that the more junior the member of the team, the higher the improvement the AI brings to them. And this makes sense because the more experienced embryologists will be building on more experience in making that decision. And therefore, the opportunity for improvement is lower. But what this highlights for me is the ability of AI to bring an equal level PEGI chance of prediction, irrespective of the embryologist's level of experience. So this now raises the junior embryologist's ability to predict the same level of the senior embryologist by using AI. And this is a very, very useful benefit that comes from artificial intelligence, the consistency in expertise being spread to every embryologist treating every patient at a global level. So consistency is obviously key, and we need to figure out how we're going to standardize the morphological evaluation across different embryologists, but also across different labs and across different countries. But what are the challenges? You know, what are the problems we're experiencing with embryo classification? Well, the first one is the fact that different clinics use a different language. Maybe we use Gardner grading, maybe we use the Vika Zaninovik, maybe we use the Istanbul consensus or the ASIBIR. So whatever method we're using, it's not an international language that the different fertility professionals can all comprehend, or even that the different patients can understand when they're looking up what it means to have a 4AA embryo. So even when the embryologists are using the same language, so in this case, it was the Gardner grading, when we provided 395 images of embryos to 5 different embryologists, and these were very experienced embryologists, we only found that they agreed in 1 in 4 of these embryos, 89 of them. And that's a very low level of consistency, which really needs to be improved. Why are we not achieving this consistency? Well, one of the things is we need to understand the limitations of the human eye. So here's an example of a limitation that we have. This is the Ebbinghaus illusion. So if I were to ask you which of these green dots is bigger than the other, you're probably going to suggest it's the one on the right. But if we remove the black dots from around it, what we find is that, in fact, our eyes were biased by the black dots and were making us think that the one on the right was bigger, when in fact, both of these green dots are exactly the same size. When we overlay this onto the inner cell mass, we can see that Ebbinghaus, the impact of the trophectoderm cells around the inner cell mass can affect our assessment of the inner cell mass itself. But AI can quantify them the way they are. AI can identify whether the 2 green dots are actually the same size or not. And this is particularly challenging for us when the inner cell mass is in different positions of the embryo. So we tend to think that an inner cell mass on the side of the embryo is better quality than if the inner cell mass is in the bottom or the top, when in fact, we would have graded them differently had the embryo been in a different configuration. So we need to kind of consider that we have limitations with our human eye, and if the computers can help us be more effective, we should consider them. There's a second problem that we have with embryo classification, and that is that the definitions that we're using at the moment. So here I have the trophectoderm definition for A, B, and C, the Gardner grading. So for A, we have many cells forming a tightly knit epithelium. For B, we have few cells. And for C, we have very few cells forming a loose epithelium. We're using words like many, few, and very few. We're using words like tightly knit and loose. So no wonder we're not really agreeing with each other with these kinds of definitions. Now, I'd love to congratulate Asibir because they have come up with a solution to this. They thought, you know what, we're going to put specific measurements, specific number of cells, specific micrometers of diameter, specific surface area, micrometers squared for the inner cell mass. And we're going to use these as cutoffs to determine whether it's A, B, or C. And the challenge we have here, and this is great because it brings the objectivity that we need so much for clinical decision making. But can you imagine how much time we would need to measure for each individual blastocyst, count the number of effector cells and measure and get the surface area? It's slow, it's complicated, and we need something simpler. Now, artificial intelligence can take this into account and can measure this automatically for us, and then come up and tell you, well, actually, this is an A based on the level of compaction, based on the surface area, based on the diameter, and so on, and provides you with a quantifiable, objective, simple, and fast way to do this assessment. So this example is Chloe from Fertility, and this was presented by Dick Sales in the Spanish Society meeting, and they found that the agreement between the embryologist grading and the Chloe grading was 87% in agreement. And just bear in mind that this remaining 13%, how do we know what's the ground truth? Is the embryologist right or is the AI right? But it's amazing to see that the level of agreement is so high to show that it is actually measuring something that is not that different to what we have been looking, but it does it faster, it does it more objectively. It can also quantify for us things that we've never had time to look at. We have all these publications looking at various features of embryo development, and we know that they are predictive of implantation, but we can't logistically incorporate it into our embryo selection methods if we're doing things manually, such as the ratio between the inner cell mass diameter and the blastocyst diameter. But the AI can quantify this for you automatically, saving you time and increasing the amount of information you have at your disposal. Another example is collapses. We know that the number of collapses and the extent of collapse is a great predictor of implantation, but we don't have the ability to quantify this. But now we do with artificial intelligence. So Chloe is able to quantify exactly how many collapses have happened, at what time points they happened, and what percentage shrinkage the embryo has shrunk by. So Chloe stands for Cultivating Human Life Through Optimal Embryos. And Chloe comes from Fertility and is the first and only transparent AI assistant. And the idea is to support the decision making. It's not making the decision for the embryologist. It's there providing extra, it's simplifying information that's coming from the complex time lapse into numbers that we can now make decisions for this particular embryo. So an example of how AI can be used to support decision-making. So Chloe has the following functionalities. It can do the automatic PN assessment. So it can tell you automatically how many PNs, 0, 1, 2, 3 PN embryo. It can differentiate between pronucleates and vacuoles. And it can identify whether the zygote has degenerated as a consequence of the ICSI. This can bring us a little bit more control on the day one assessment, saving time during that assessment. It can also detect cleavage anomalies that would usually be missed, things like direct and even cleavage, severe fragmentation. It can identify and provide a score or prediction. What is the chance that this embryo is going to form a blastocyst? What is the chance that this blastocyst is going to implant? And what is the chance that this blastocyst is going to be euploid? So it can provide these predictions for you in easy scores as early as 30 hours post-insemination. Okay, and I will show you some of the work that we conducted to determine what is the level of efficacy or prediction. It can also do automatic annotation. So all this time that we spend annotating embryos, we no longer need to do that. And it can track the inner cell mass, it can track the embryo development, and it can track the blastocyst grade. It can also provide the automatic morphokinetics. So here's an example of how it does. With the overlay, you can see the automatic identification. It shows to you how it's making that assessment. So if it's highlighting a vacuole, you know that that's incorrect. But in fact, you can go in and say, well, actually, yeah, that's a PN I would have missed, and it highlights it to you. It goes through each of the cell divisions and shows the time points, and it actually shows whether these time of cell divisions happen in the normal range or not. demonstrating what are the good and poor things associated with this embryo. It can track the inner cell mass, it can highlight the trophectoderm cells and counts them. And all of this it can do, automatically for you, not requesting it to do it, it's just doing it automatically for you. So we've done some assessments with some embryologists from around the world. So here's the data from the assessment with Amy Berry. Amy Berry is from Care Fertility. She's the head of labs there. And she did the assessment where she demonstrated that the PNs are the level of agreement between experienced embryologists and the human is at least strong. And for most of these morphokinetic parameters, it is very strong. This has been replicated with a number of other clinics as well. So here we have 6 independent clinics where we're comparing the level of agreement between Chloe and experienced embryologists. And you can see that throughout, it's either strong or very strong for all the morphokinetics. The level of agreement is very high. One of the publications that is going to be presented at ESHRE this year is coming from Next Clinics, where they used Chloe to assess all the embryos they've had historically and to see how the morphokinetic differed between embryos that were utilized, transferred, or cryopreserved, which are in red in this graph, and embryos which were discarded, which are in blue. So on the x-axis, you have each of the morphokinetic parameters, and on the y-axis, you have time, hours post-insemination. And you can clearly see that there's an optimal range for embryos that are utilized. And what we find is that by using Chloe, you can automatically make this assessment and determine whether this particular embryo is within that range. For PN assessment, we have done some work with Juana Crespo in Spain, and they demonstrated that they agreed with the accuracy of PN assessment, 93% of their embryos. We know from the assessment of direct and even cleavage as well that this is something that sometimes we don't have time to see or is easily missed. And with this pink logo therein, we can see at a first glance, this embryo has had direct and even cleavage and severe fragmentation. We also know from the time point that it's outside the normal range because the arrow is on the red bar rather than the green. So at a glance, it kind of highlights to you there's some issues with this particular embryo. The inner cell mass can be tracked and the surface area can be quantified. We can also look at things like the roundness and the level of compaction, the ratio between the inner cell mass and trophectoderm, automatic blastocyst grading, embryo diameter, collapse percentages and time points, collapse numbers, and all the time points from all the various morphokinetic stages. The system can also provide insights that reduce the chance of the embryologist missing key information. So it will highlight that, this particular embryo is a direct and even cleavage. This particular embryo has had severe fragmentation. The T7 for this embryo is outside the normal range. So it will highlight some of these issues. But it also does the other way around, as you can see in this example, where it provides you saying this embryo has good morphological score. This embryo is the best candidate according to our AI score for transfer, and we didn't find any issues with it. How reassuring is it to be able to have that information and contrast it with others where issues were identified? And that reassurance is also very important when we're making our decision. So what about prediction of blastulation? It can do this prediction as early as 30 hours post-insemination. And we have done this assessment in 6 different clinics with an overall level of accuracy of 0.86. And it varies from 0.84 to 0.93 with the area under the curve. So the level of accuracy of prediction as early as 30 hours post-insemination is very high. We have done some work with Juana Crespo as well, where they looked at the blast prediction score and clearly demonstrated, as you can see on the graph on the left, that the quality of the embryo on day 3, was clearly correlated with the score. We could also see that the Chloe blast score on the graph on the right was clearly associated with blastulation. And for this project, we looked at prediction of 44 hours, and the level of the area under the curve was around 0.84. If we looked at prediction of blastulation or 0.81 if you want a prediction of oscillation by 116 hours. So just to show that it's not random figures that the AI is throwing out there. These are biologically relevant figures that we can use to improve our decision making. We can also use the system to rank embryos. Which one should we be considering for treatment first over another? And we have made an assessment with Juana Crespo that the agreement between embryologists and Chloe with regards to ranking is around 75%. It brings into question the remaining 25%. Is it that Chloe is better, or is it that the embryologist is better? And this, we're already planning to do some trials to answer that question. On the red line here, what we're looking at is the area under the curve. So what is the efficacy of prediction at various time points is what you have on the x-axis. So what we see is Chloe is the red line. We can see that as time develops, the prediction level from about 40 hours to around 100 hours doesn't really increase. But beyond that point, now we're seeing the blastulation happening and the expansion of the blastocyst. The more time that the embryo is in the incubator, the higher the ability of the AI to predict whether this embryo will implant or not. And what this highlights to me is the importance of having the embryos cultured all the way to blastocyst stage all the time, irrespective of how many embryos they have in culture. And I'd like to reference here the Cochrane review that Christian Sedal has published recently. So your fellow Peruvian, really looking at blastocyst culture versus cleavage culture. And for me, this is another argument to say that blastocyst culture should be the norm. AI can also help us save time. It's not just about ranking embryos and telling us which embryo to pick up. It's also about saving the embryologist time. And I wanted to bring to your attention a few statistics, which are the reality. It's a type of statistics we don't talk about much because they're not really basic embryo biology. But I think the embryologist biology is equally as important. So we know from the work conducted by the ASRM and published in 2018, and the works conducted by the British Embryology Society, ARCS, in 2021, has clearly demonstrated that embryologists are highly stressed. 89% have mentioned that they have high levels of stress at work. We have 24% have actually, which is 1 in 4 of us, have reported that they suffer from mental health because of work. And the level of pressure that we have in the embryology lab is not something we talk about much, but it's something that we should be talking about, because these are things that are leading to human error. And these are things that we need to bring certain technologies to support the embryologist better. And one of the things that's causing all this stress is the fact that we're all overworked. We don't have enough embryologists to do the work and the workflow that we've created. So maybe what we need to do is simplify that workflow. Maybe what we need to do is introduce technologies such as time-lapse. Time-lapse has improved the workflow immensely in terms of streamlining, bringing flexibility in our work practice, and allowing the embryologist to work remotely where possible, but also to not have to be there 24/7, because the camera of the incubator is there 24/7. So the embryologists can work much more efficiently because they have time-lapse. Now, if you bring time-lapse together with AI, it's a whole new level of improvements that we bring to save the embryologist time, yet make them more effective. So bringing AI and time-lapse together will increase the capacity of cycles that each embryologist can treat, whilst reducing their stress, whilst reducing the errors associated with being overworked. It will increase the efficiency in the lab, and hopefully this will retain the good embryologists in your clinic, because they're not going to want to leave, because embryology is an amazing job. And if we can find a way to reduce the stress associated with it, we should, to give it the best of both worlds to every embryologist out there. So what we have is with Chloe is not just the ability of it making all these assessments, but also, for instance, when it assesses the number of PNs or what is the grade of the embryo, it can automatically input that information into the EMR. So your electronic medical records is always complete, it's always accurate, and the information is coming directly from the source being the time-lapse incubator. So we now have direct integration from the time-lapse incubator into Chloe, direct integration from Chloe back and forth to the electronic medical records. And this now provides no need for you to write down notes on a piece of paper, no need for you to type up in the EMR, and the amount of time this saves shouldn't be underestimated. So I looked in my clinic, what are the key steps that are happening when we're making the embryo assessment. And the step one is that we look at the embryoscope, and we have another computer on the side, as you can see here on step one. This is Tom, and Tom is looking at the embryos, and he's annotating the embryo development. He then writes it down on a piece of paper. What is the grade? What is the fate? Which embryo should be cryopreserved or not? And then later on, Tom's goes to a computer and inputs it into the EMR. And later on, either Tom or another embryologist gives a call to the patient or a call to the clinician to explain what has been seen and what should be the next steps. Now, these are 4 steps that when you have this direct integration between Chloe and the incubators and Chloe and the electronic medical records, it becomes 1 step. Within 1 step, the patient's informed, and we can still make the phone call, but we don't have to send reports. We don't have to input manually on the EMR. We don't have to write down what is the grade of the embryo. So we have here, this is replicated multiple times in each cycle. Okay, we do this daily in our clinic. And when we look at all of these steps, which are in red, all of them can be automated by Chloe. Okay, the ones in dark gray are the technical procedures. So when you look at life post Chloe, you can see that we're no longer doing administration. We are there enjoying our life as embryologists, working on the technical aspect and working on the clinical decision-making, which are the bits that we enjoy. And it just becomes a more enjoyable job by not having to do paperwork. But it's not just about being enjoyable, it actually saves our time. So each of these steps carry an amount of time, with or without Chloe. So when you use Chloe, it actually saves about 3.33 hours per cycle. It's a third of your time that can be saved by automating these steps. And when we convert these hours into number of embryologists that you have in the team and the number of cycles capacity per embryologist, for each of the cycle, depending on the size of your clinics, as you go down this table, the size of the clinic increases. We can actually demonstrate an increase in the percentage of capacity of cycles per embryologist of 50% increase. I mean, this is quite dramatic. So to be able to have such a big increase in, what are we going to do with that the rest of the time? We're going to treat more patients. We're going to speak with the patients, and we're going to personalize their care further than what we're currently capable of with the time we have available. But it's not just about saving our time, it's actually reducing the risk as well. So if you look at the time that we spend on mundane tasks, this is reduced by 33%, but the time that we are spending on now the patient is going to increase by 50%. But let's look at the risk aspect. So we did a failure mode effects analysis, and this involves, number one, we identify all the steps of the process. We identified 8 phases, which are part of the embryo selection process. We then identify where things can go wrong, so these are failure modes. And of these failure modes, we then look for the causes of that problem, the consequences. We quantify what is the probability of this failure happening, what is the severity, and what is the detection level. And lastly, when you multiply these numbers together, it brings you the risk number. So with this risk number, we can now rank which risks require mitigation or not. So if you look at those 4 steps of when we are assessing the patients, that we annotate, and then we write it down, and then we contact we put it into the electronic medical record, and then we call the patient. Those are the 4 steps. In each of these steps, there is an opportunity for error in transcription, or where we miscommunicate the information, or ultimately this could lead to us choosing the wrong embryo. So we know that humans do a mistake of on average 1 in 100 times that we're writing something down or typing something down, we will mistranscribe. So if we mistranscribe a 4AA into a 4AC, that's a completely different decision of which embryo we should be transferring back. And we will be doing that mistake about 1 in 100 times. So what we need to do is remove this opportunity for error, which the machine, by taking the information directly from the source of the data, would not have these types of errors. We also went down to look at the risk levels and for each individual failure mode without Chloe and with Chloe. And where we see the benefits is that 50 of the failure mode levels were eliminated completely, leaving only 30 behind. We also see that those that were left behind, the failure levels of the risk were reduced. Okay, and we see that the highest risk level reduces from 36, which is high, to 16, which is moderate. So in conclusion, for this section, we know that the manual annotations need to be replaced with automation. We know that we need to eliminate areas of our workflow that are bringing redundancy. And we know that we need to look for opportunities to reduce the risk of human error. There are other examples out there where AI is being used to reduce risk. And I love this example. It's from my colleague, Charles Borman. He presented this in ESHRE 2021, and I found this very inspirational. So his project, he looked at the embryos in time lapse, and he tried to match them with embryos later on. So he looks at the fingerprint of the embryo to see, can we use this as a witnessing tool based on the image of the embryo? A fantastic and very creative use of the system. And if we were to incorporate this into the other microscopes or outside the time-lapse system, the opportunity is that we can now track individual embryos as we are moving them from dish to dish. If you look at this example, this is just the example of tubing and biopsying an embryo, how many times removing these dishes, how many opportunities we have to end up putting the wrong embryo in the wrong straw, or mislabeled the biopsy tube. But this technology that Charles Borman has presented paves the way for us to be able to use image analytics to witness the embryos based on the fingerprint of the image of each individual embryo. It's very important that we implement artificial intelligence responsibly. Okay, and this is the work that was made by my other friend and colleague, Nikika Zaninovic, who's also one of the organizers of the AI Fertility Conference in Croatia. And Nikika sent about 500 or so embryos to 5 different embryologists, but also 5 different AI companies. 7 different AI companies, and asked them to rank these. And what he found actually is that the embryologists agreed with each other more than the AI companies agree with each other. In fact, some of the AI companies were providing random results when it came to determining which embryo should be ranked first or last. So it's very important that we validate whatever AI tool we're using. Do not just use an AI tool based on the data that the company have provided. Test it on your own data and see how it performs with your own data. And this is very important, that we have a robust validation system before incorporating these tools into clinical practice. The risks are therefore not with the technology itself. AI is not the one carrying the risk. The risk is with us and how we choose to implement this innovation. So we need better standards. I would urge the Peruvian Society and all the other fertility professional societies out there to create standards that we can all follow to ensure we are validating these technologies correctly. We're biologists, we're doctors, we're not mathematicians, and it's important that we have these standards to support us in assessing these technologies in the correct manner to protect our patients. So in conclusion, AI is ideally suited to automate and standardize subjective, time-consuming aspects of time-lapse. And we have to understand that ranking is very helpful in terms of helping us select which embryo to transfer back. But ranking embryos in order of priority for transfer is not really enough. What we need is to build trust in these systems, validate them effectively using our own data. But we also need to understand how it's reaching that decision, how the AI is making the suggestion to me in terms of choosing this particular embryo rather than an alternative one. We need AI solutions that are going to turn the black box into a glass box. We need transparency. We need transparent AI that can explain not just the mathematics, but the biology. I don't understand the mathematics of AI, but I understand the biology. And if the AI can explain to me transparently the biology in a way that I can understand, in a way that I can make my decisions to the best standards to treat the patient, that's what we need. So thank you very much for your time. I really believe that IVF will never look the same again. Thank you.